Dr. Richa Sharma, Assistant Professor in the Department of Electronics and Communication Engineering, Punjab University, Patiala. The topic of today's video lecture is Static VI Characteristics of PN Junction Diode. Here in this video lecture we will cover what do you mean by zero biased junction diode, reverse biased junction diode, forward biased junction diode, characteristics of PN junction diode, then what do you mean by knee voltage, breakdown voltage, and what is the difference between knee voltage and breakdown voltage, Zener breakdown and Avalanche breakdown. We will discuss all these one by one. First of all, there are two operating regions and three possible biasing conditions for the standard junction diode. The first one is zero bias, when no external voltage potential is applied to the PN diode. If I am talking about a PN diode, let's say this is my PN, when no biasing is applied here, that is called zero biasing. And when reverse bias means the voltage potential applied, the voltage potential is connecting negative to the P type material and positive to the N type material across the diode, which has the effect of increasing the PN diode's width. Means if we are having a PN diode, this is my P and this is N. In the case of reverse bias, the P is connecting to the negative of the battery and N is connecting to the positive. This is negative, this is positive. P is connecting to the negative and N is connecting to the positive. And in the case of reverse bias, this depletion layer is wider, as I have discussed in the previous lecture. And the third one is forward bias. In the case of forward bias, voltage potential is connecting positive to the P type material and negative to the N type material across the diode, which has the effect of decreasing the PN junction diode width. Here we are having the depletion layer is narrow. Now we are discussing zero biasing in detail. As shown in this diagram, we are having this N region, this is the N region and this is the P region, and there is zero biasing, no battery is connecting to the this PN junction diode, and this is the symbolic representation. This is the symbol for the diode, and here a resistance is connecting, and this is how the circuit is shown for the zero biasing. What do you mean by the zero biasing? When a diode is connecting in a zero bias condition, no external potential energy is applied to the PN junction. Here we are not having any voltage source across the terminals. However, if the diode terminals are shorted together, a few holes from the P type, which are the majority carriers in the P-type material with enough energy to overcome the potential barrier, will move across the junction against this barrier potential. This is known as forward current and it is referred as IF. This is IF because when we are not having any external potential energy across the PN junction, some majority charge carriers from the P type starts moving towards the N side and it overcomes the potential barrier which moves across the junction, and the current because of this is called the forward current and it is denoted by IF. Okay, so likewise holes, as in the P type, holes are the majority charge carriers, they are start moving towards this, and the electrons are the majority charge carriers, they are start moving towards this. And here in the P type, majority charge carriers are hole and minority charge carriers are electrons. Similarly here the majority charge carriers are electron and minority charge carriers are holes. Okay, so likewise holes generated in the N type material find this situation favorable to move across the junction in the opposite direction, and this is known as reverse current, and it is referred as IR. This transfer of electrons and holes back and forth across the PN junction is known as diffusion. Basically, when we are not having any external source, their diffusion of the electrons and the holes take place, means majority of the charge carriers from the p type are moving towards the n carrier, and majority of the electrons from the n type are start moving towards the p type. Then reverse bias PN junction diode. Now look into this diagram. This is the condition when we are having the voltage source across here, when this N is connecting to the positive terminal of the battery and this P is connecting to the negative terminal of the battery. This condition is called reverse biased condition, and in this condition we are having the wider depletion layer. Wider depletion layer opposes the flow of the current. Because of this wider depletion layer, no current is flowing in the diode. Now, when a diode is connecting in a reverse bias condition, a positive voltage is applied to N-type material and a negative voltage is applied to the P-type material. The positive voltage applied to N-type material attracts electrons towards the positive electrode and away from the junction, while the holes in the P-type and are also attracted away from the junction towards the negative electron. Because of this depletion layer is getting wider and wider. The net result is that the depletion layer grows wider due to the lack of electrons and holes and presents in a high impedance path, almost an insulator, and a high potential barrier, this is called high potential barrier, is created across the junction, thus preventing current from flowing through the semiconductor material. Because of this wider junction, no current is flowing in the reverse bias. This is the graph for the reverse bias. In this this reverse breakdown voltage I will discuss later on, and this is almost zero current is flowing, and this is called reverse biased region, and the reverse current is denoted by IR and the voltage is VR. Then forward bias PN junction diode. This is the diagram for the forward bias. In the forward bias, the P is connecting to this P region is connecting to the positive terminal of the battery, and N is connecting to the negative terminal of the battery, and this condition is called forward biasing, and this is the symbolic representation, and in this case the maximum current is flowing, and that is why in this condition the depletion layer is very small, and because of that small layer the maximum current is flowing. Now when a diode is connecting in a forward bias condition, a negative voltage is applied to the P type material and a positive voltage is applied to the P type material. Okay, and if this external voltage becomes greater than the value of the potential barrier, approximately 0.7 volt in silicon and 0.3 in germanium, the potential barrier opposition will be overcome and current will start to flow. Means that if external voltage, the voltage we are applying here, is greater than these values, because for silicon we are having 0.7 volts and for germanium we are having 0.3 volt. If this value increasing these values, the potential barrier opposes the barrier here, it opposes to overcome, means the barrier is overcome and the current starts flowing in this case when the voltage value reaches greater than this value. This diagram shows the graph for the forward current. Here it is almost 0. When it reaches the value 0.7, it starts increasing. This is called forward bias region, and this is for the silicon diode. If it is for the germanium diode, then it will start here at 0.0 at 0.3 volts. Then this is because the negative voltage pushes or repels electrons towards the junction, giving them the energy to cross over and combine with the holes being pushed in the opposite direction. Means the electrons are pushing from here and the holes are pushing here, and because of this this results in the characteristics curve of zero current flowing up in this voltage point. This is called knee voltage, the point where it starts increasing from 0.7 or 0.3. That voltage is called knee voltage on the static curve. And then a high current, this is high current flow through the diode with little increase in the external voltage. This is the combined static VI characteristics of PN diode. Now I am explaining this. This is the PN junction diode, and this is the symbol, and this is my cathode, and this is my anode. And here we are having the forward biasing and reverse biasing. And in the forward biasing, as I have already told you, that in the forward bias the current is flowing and the P is connecting to the positive terminal of the battery and N is connecting to the negative terminal of the battery. In this condition, when it crosses 0.7 volt in the case of silicon and 0.3 in the case of germanium, this is after that abrupt current starts flowing. This is called the rapid rise in the forward current, and the point where it starts rising, that is called knee voltage. As I have told you, 0.3 for germanium and 0.7 for silicon. So this is my forward condition. Then in the negative, in the reverse condition, we are having the PN diode, and P is connecting to negative and N is connecting to the positive. And here this is the leakage current, very low current is flowing, and this is the reverse breakdown voltage. A point comes when the this depletion layer is getting wider, and all of a sudden it starts break, and at that point it is called breakdown voltage, and the current is flowing like this. I am explaining this part in the next slides. Okay, so this is the VI characteristics of PN junction diode. Now, first of all, knee voltage. What do you mean by the knee voltage? This is the knee point, knee voltage. In the forward characteristics of a diode, once the voltage is applied, then the junction starts increasing rapidly. It is known as knee voltage, and an alternate name of this is cut-in voltage. This is also called cut-in voltage. Knee voltage for silicon and germanium. For silicon it is 0.7 volt and for germanium it is 0.3 volt. So this is the knee voltage. Then breakdown voltage. Breakdown voltage is when PN junction diode contains a band gap through which exchange of charge carriers take place. When a forward bias is applied, current flows in the forward direction and conduction takes place. It is the normal condition. When we are forward biasing the diode, the current is flowing in the forward direction and conduction is taking place. But in the case of reverse bias, when a reverse bias is applied, no conduction should take place. Why? Because of the because of the depletion layer. Because in the case of reverse bias, the depletion layer is getting wider. but due to the presence of minority charge carriers, a small reverse current flows through the diode known as leakage current. As in the previous slide, this is the leakage current. The minimum current flowing in the reverse direction is leakage current. Okay, due to the flow of the reverse current, the current that is called leakage current, the width of the junction barrier increases. When this applied reverse bias voltage increases gradually, the voltage which are applying in the reverse biased, when it increases gradually, and at a certain point a rapid increase in reverse current can be observed, as I have shown you here in the previous. Here, this is the abrupt change in the reverse current. So this is called reverse breakdown voltage, where the current value increases. This is the leakage current, and after this breakdown point, the current starts flowing rapidly. Okay, so the corresponding applied reverse voltage at this point is known as breakdown voltage. The point where the large amount of current, rapid current is flowing in the reverse direction, that voltage is known as breakdown voltage. Okay, this is also called reverse breakdown voltage. Then what is the difference between knee voltage and the breakdown voltage? The forward voltage at which the flow of current during the PN junction begins increasing quickly is known as knee voltage. This voltage is also known as cut-in voltage. This voltage is least reverse voltage at which the PN junction can behave without harm to the current. Then it is the position within the forward bias of the curve wherever the conduction begins to rise quickly of the PN junction diode. Means that after this knee voltage, the conduction starts quickly. Then the diode's breakdown voltage can be defined as the least reverse voltage which is used to make the diode perform in reverse. Breakdown voltage is a factor of a diode that describes the highest reverse voltage. This voltage can be used without affecting an exponential rise in the current of the diode. Means that when the reverse voltage increases, a point reaches when the abrupt current starts flowing. So next is the definition of Zener breakdown. What do you mean by Zener breakdown? This is the symbol for the Zener breakdown, Zener diode, and in the forward direction it behaves like a normal diode, but in the case of reverse it works differently. Zener diodes are used as basic building blocks in the electronic circuits. They are popularly used to provide reference voltage to the electronic circuits. They are designed to work in the breakdown region of the diode. This is the main specialization or special character of the Zener diode, that Zener diodes are working only in the breakdown region. Zener diodes are heavily diodes that can work reliably in the reverse biased regions. Here breakdown takes place due to Zener effect. What do you mean by Zener effect? In the Zener effect, when electric field of the reverse biased PN junction is increased, tunneling of the valence electrons into the conduction band takes place. This leads to an increase in the minority charge carriers, thereby increasing the reverse current. This phenomena is known as Zener effect, and the minimum voltage at which this phenomena starts is known as Zener breakdown voltage. The voltage at which the breakdown occurs is known as Zener breakdown. And why the breakdown occurs? Because of the Zener effect. And what do you mean by the Zener effect? Zener effect is basically when electric field of the reverse current, this is the electric field of the reversed biased PN diode, is increased, and because tunneling of the valence electrons into the conduction band takes place. This leads to the increase in minority charge carriers, thereby increasing the reverse current. Because of the minority charge carriers, a current flowing, that current is called reverse current, and this phenomena is known as Zener effect. Hope you understand what do you mean by the Zener breakdown, and this is called Zener breakdown region. Then avalanche breakdown. Avalanche breakdown. In lightly doped diodes, breakdown takes place due to the avalanche effect. When the breakdown occurs due to the Zener effect, as I have told you in this slide, Zener effect, that is called Zener breakdown, and the breakdown occurs due to the avalanche breakdown, that is the voltage is known as avalanche breakdown voltage. What do you mean by avalanche breakdown? In lightly doped diodes, breakdown take place due to the avalanche effect. Here in the avalanche effect, when a diode is operated in the reverse bias, due to the increased electric field, the minority charge carriers gain kinetic energy and collide with the electron hole pair, thereby breaking their covalent bonds and create a new mobile charge carrier. This increase in the number of minority charge carrier leads to the increase in reverse current, causing breakdown. Here the breakdown voltage is known as avalanche breakdown voltage. Means that because of the avalanche effect, what do you mean by avalanche effect? In the reverse bias, when the electric field is applied, the minority charge carriers present in the minority charge carriers gain kinetic energy, and because of high kinetic energy, they collide with the electrons and holes. Electron hole pairs collide, thereby when they collide, the covalent bonds are breaking. Because of the breakdown of covalent bond, there is an increased number of minority charge carriers, and as the minority charge carrier increases, the reverse current increases because of this breakdown. So this is avalanche breakdown. Hope you like this lecture, you understand this lecture. Thank you very much, and do subscribe my YouTube channel for more lectures. Thank you very much.